3.5 yet. But then you start to look at that step 2 that I mentioned at the start. You start to drill into the cross-sectional area of a tower. That comes in stage 2. We're still in stage 1. I just wanted to give you some idea that there isn't a assessment criteria that you put together. Let's get straight into the case study. The case study is, I just want to give you a bit of a background and history here. You can see it in front of you. It's a single circuit 330 steel tower line. It was constructed in September 1961. It's over 55 years old. Absolutely, it's a self-supporting structure. That, in other words, are not stayed in any way. There's no recorded failures. In 1974, there was, as happens with a lot of our older lines when they're first built in the 1960s, they had to be upgraded to increase capacity to meet the needs of the growing population, if you like. Additional 23 structures were installed in 1974 to increase its operating temperature from 95 degrees Fahrenheit to 220 degrees Fahrenheit. Obviously a large increase in capacity. Just so you've got some idea, it's at 68 kilometres long. The 1961 towers, 154 range of suspension and tension towers. The additional 23 structures that I mentioned above, the line has a total of 177 towers. I just wanted to bring to your attention here, here's the spatial route alignment of the line that we're looking at today from Sydney South to Dapto. There's a middle section which I've marked there in yellow. It's important that as we go through the visual rating process, it gives you an appreciation of the level of deterioration of that third of the tower in the middle. As you can see, it's close to the coast. It's about 4 kilometres from the coast there. And the other thirds to the north and to the south are moving away from the coast. And it's quite significant, so you can appreciate the deterioration that we're talking about. And again, as an asset management, where you should be focused. The visual rating was performed on this line, all the towers, and as you can see, there's a condition assessment or a VR profile for the line. I just want to let you know that that was done with 2 professional young engineers who went through it in a day. They transferred each other's assessment of the towers, and any discrepancy in the visual rating, they agreed to disagree, and they came up with the numbers. So it was a very simple process, very quick, again, turning data into useful information. Let's see how we can turn that data into useful information. As I just wanted to highlight there, you'll see down the bottom, 3.5, none of these towers, even after 55 years, have any structural integrity issues. This here, I've mentioned to you, this is a suspension tower, and this is outside that middle section. Just so that people understand what a suspension tower is, it's a way that the insulators are supporting or holding the conductors. That's in a suspension mode. They're not cut, they're actually being supported. The second thing I wanted to highlight to you was that the chords of the tower, the primary members are the big, thick edging outlines. It's not the thinner, smaller bracing in between those primary members. So the primary members, as you can see, come up from each leg. They're large. They come up through to the waist. They break up to the cross arms, and you can see those large cross-sectional areas. They're the primary members. The much smaller ones in between, as I said, they're redundant, if you like, secondary members, and they're bracing the primary members. As I said, the structural integrity, 99% of the work is being done by those primary members. This now is a middle. I'll just go back to that one. As you can see, the visual rating on that tower is a VR2. That tower is over 55 years old, and it's in a relatively good, sound condition. This is now a tension structure. As I mentioned to you before, look how the strings are. They've been cut, they've been terminated. That's a tension tower. There's a lot more load. Typically, a tension tower is an angled structure. They've got to take a lot more load. They're a stay-type structure. In other words, if you lost conductors, these structures are designed to hold onto those conductors. They're a much broader, bigger structure. Traditionally, they're the smaller of the two. They might say that in height, but 2 or 3 times the weight in steel. And the foundations are larger, of course, to handle compression and uplift. This tower here, again, is outside the middle section. It's got a VR2. On the tension tower there, you can still see those strong primary members. Again, the legs coming up to the waist and the heavy superstructure at the top that joins onto the cross arms and earthwire pegs. As you can see from that visual rating, 55 years old, still very, very sound condition. Now we're in the middle section. This section that I mentioned to you is within 4 or 5 kilometres of the coast. This is one of the higher VR3. That's a suspension structure there. You're starting to see the heavy rust or the loss of galvanising on the structure. Very strong at the top part of the structure. You can see around the earthwire peaks and the top of the crossarm, heavy rusting there, and as you work your way down the tower, you can see now that the primary members, again, that's the area that we're looking at, primary members, not so much the secondary members, are showing signs of loss of galvanising. We're starting to eat into the structural steel. This is one of the 1974 towers. It's a suspension tower. Surprisingly, this was put in, like I said, around about 14 or 15 years after the original 1961s. And it's a 2.5, so it deteriorated significantly in that middle section as well. Even though it's 14 or 15 years younger than the others, you can start to see now that the heavy corrosion at the top of the tower, again, this is just a desktop assessment, but it's starting to give you a focus on where you need to look. You can see there that the structure, I believe that the galvanising might not be galvanising. When I say that, you know, oil ain't oil. Basically, the galvanising of the 1961 towers may well have been thicker or it's a better product than the actual 1974. That's only a hypothesis, but reality is it's deteriorated a lot more than one would expect. This is now a tension structure in the middle section. You're starting to see the size of these structures, heavy corrosion on the main superstructure, which is a crossarm, earth wires, down to the waist. Pretty much the tower's now starting to show signs on the primary member that it's losing its galvanising. It's getting into those areas where we need our attention as asset managers. It's a VR3. What we've done now with that data, we've turned that into, as we said before, a condition asset profile. These are the 1961 towers. The reds are the tension, the blues, bluey greens are all the suspension. You'll see there's a dip in that middle section. The reason they've come down to a 1, a lot of those are suspension towers, they were painted, and they've got a visual rating of 1. Well, that just gives you some idea why there's that dip in the middle. As you can see, they've paid their attention in that third. If you look in the middle part between structures 31 and 40 through to about 105, you can see that they're starting to get this pyramid effect in the middle. You can see that the extreme thirds, both to the north and to the south, are in a lot better condition. They're relatively 2s, and the middle section of 1961s around 2.5, and some are now hitting the 3. Certainly a lot of suspension are, and a couple of tension. Here's a snapshot of the 74 towers. As you can see there's not as many of these. The 23, the blue one is the one tension structure that they put in, all the others are suspension. Again, a couple there in the middle hitting 2.5, but generally they're below 2 or below. Condition assessed profile, these are all the suspension towers now put together. You're starting to get now a real feel for that pyramid effect in the middle. You can see all those suspension towers that are hitting 3s are all in the middle section. Here's the tension towers. As I said, there are not a lot more of them. You can see a lot of tension towers at that front end, or the northern end. That's because of the route alignment, moving around various pieces of infrastructure to get the alignment for the line. After that, it goes relatively straight or in long sections. You can still see those 2 heavy tension towers in the middle that are hitting the 3s. Here's now we've combined all the structures. Again, there's that pyramid. It's only a desktop assessment, but it's given us now the opportunity to look at that part of the line that really needs our attention. You can't look at 177 every year, but all of a sudden you're starting to get a feel for where attention as an asset manager you should be focused now. And clearly those ones that are hitting 3s, all in the middle section, need our attention. Just want to give you an observation. This is the observation, the findings. Basically, the middle section consists of 50 to 60 towers, 3 to 4 kilometres from the coast. Obviously, salt-laden winds and heavy fog in that area causing the deterioration. Overall, that middle section has a much higher VR rating than the other 2/3 of the line. What was an observation is at the top of the steel towers, with a part that you can't see when you do route patrols, you've got to be above the tower, hence the drone or the helicopter and digital cameras, gives you a really good detail that deterioration is happening at the top of the tower where the salt is laying, the moisture is there, and of course corrosion is allowed to happen. Surprisingly also, the seaward facing side was the one that was deteriorating the highest of the 2 sides. Clearly, once again, as asset managers, this data has been turned into information. Our focus is on the middle section. We've got 22 suspension towers and 2 tension towers that are up for question. So that's where our focus should be. What we've put together now is a bit of a financial model for you. These are the tension steel towers. What we've looked at is the blue is a 15-year painting program, the red a 25-year painting program, and the green is a replacement. Now, all these were based on a like-for-like arrangement when you're looking at replacements as we go through this financial assessment. The tension towers were relatively low VR, which is a good thing. It didn't really make a great deal of sense when you look at the difference between the red and the green. This is on a like-for-like basis, that there's not much between it, that because of the smaller number and the volumes involved, that you would really start to consider refurbishing these tension towers. I should mention that to replace a tension tower with the constraints of an easement is extremely difficult to do so. To be able to replace a tension tower, you've got to take all the physical loads off the towers, remove them, new footings, new towers, and you put the conductors back up. It's a major piece of work, and if you have to do deviations to keep the supply going, you can understand the complexities of trying to replace a tension structure. Now, this is a suspension structure. Again, the same colours as the other one. 15 years is the blue, 25 years painting is the red. And the replacement value, you can see the gap between the red and the green now is quite significant. That is, you're better off investing in replacing these suspension towers for the value that you obtain. As you can see, it just runs away the blue line. And this is on a like-for-like basis. If you look at the investment there, $20 million, reality is that if you looked at an alternative other than a steel tower replacement, which you can do, it's quite financial, you might well be able to reduce that by 50%. It's that sort of savings and that sort of thought that comes with making those sort of decisions. Summary of the case study, basically, refurbish the tension towers. There's 42 of them. It's well worth the effort of blasting them, cleaning them, and painting them and maintaining them. And look, with the tension tower, unless the capacity increases, you're talking about perpetuity here. Remember, we're talking about the above ground condition of the towers, not the below ground. That's a separate study altogether. But we're just looking at what we can see for the above ground, which is 90% of the tower. It made sense to refurbish the tension towers. The replacement complexity alone, they're talking $600,000-700,000 to just name a figure for a standard tension structure, and again, at low numbers. When we look at suspension towers, they're managed, the idea there is to basically replace them, but you don't have to replace them today. We're talking about a deferred replacement program. This is where stage 2 comes in. That is, as you start hitting those high numbers, the 3.5 VRs, you start going down a different avenue of investigation. You start measuring cross-sectional areas of certain primary members and determining, again, as asset managers, managing the risk of those towers. So that when you do a replacement program, you're hitting the focus on those 22 structures that are now hitting up that top end in the middle that we talked about. Again, like I said, that was a like-for-like. You could easily replace these structures with a concrete or steel equivalent, possibly horizontal Vs. Again, you could save 50% of probably a like-for-like replacement. Future work and improvement, as I mentioned to you, stage 2. No one's moved down to stage 2 yet. The whole idea is that, as we mentioned, it was a deferred program. There's plenty of time to start getting your head around it, and you would build up your family. But basically, the intention was that over 5 yearly programs, for example, it doesn't have to be 5, but I'm thinking 5 is a period of normal cyclic review. You start measuring deterioration of the VR ratings of those 22 structures, or the rest of the family, if you like, but those top 22, and then you start going into stage 2, which is measuring primary members. You model the structure then in PLS Tower, and you start to work out the levels of deterioration of certain members at the top and working your way down to the base. As we mentioned, a lot of the structural issues and deterioration were in the top half of the tower, of a suspension tower, which is only supporting strings. So it gives you an opportunity to look at how you want to manage that risk and how long you can defer the replacement cost. Based on what we're looking at here, considering the age of the towers, what the intention was there as a transmission network, why wouldn't you take on a network condition assessment for your transmission towers? It's a simple process. You get data, turn it into information. When you consider that probably Australia, for example, PowerLink, has the longest transmission network in the world, you can see some benefits to the transmission network to be able to get the handle around that, a simple VR rating. There's 2 other items I wanted to raise here, which I've seen over the last 15 years, and the steel tower painting specification and standards. It's such an important aspect for a utility to get that right. We work in quality circles. The focus is clearly on the contractor, but I see too many times people go for the cheapest price rather than the best value, and you really need a qualified, proven history contractor to be able to deliver a quality product in painting towers. Otherwise, you end up in a contractual dispute. Naturally, the QA system would be implemented. Who does that? Utilities love doing it themselves. They might well pay to bring in an independent party to do a QA on that contractor. That's not normal core business, if you like, for a utility that's traditionally doing power areas. There's structural integrity and the QA required on the contractor. Naturally, you would do an audit. There might be 1 in 10, could be 2 in 10. And of course, if the contractor's not up to scratch, then you make them do 3 in 10. All of a sudden, you're starting to inspect 1 in 5. And you put those costs back on the contractor. So a quality job will be the right drivers on a contractor, you get the right results. And it's important to get the QC right with the right contractor and the QA right to make sure that they're complying. Other than that, I just wanted to emphasise this is a visual rating system from the above ground condition. As I mentioned earlier, below ground is a completely different animal. Different type of testing, different type of regime. There are ways of protecting below ground assets, particularly foundations. Even if they're grillage foundations, there's all forms of half-cell measurements and anode protection, and all the monitoring goes below ground. But the important thing is, it's a waste painting or replacing if you don't align your strategy with below and above ground. I'm just showing you a simple tool for a visual rating above ground. That's it.
Thanks, Colin. I have unmuted everyone, so hopefully you can all hear me.
I can hear you.
Good. Colin, that was very interesting. Thanks for that. Firstly, I need to apologize. When I mute everyone at the beginning, I believe I mute you as well because you got two accounts under the list. So we probably missed your speak on the first slide. Hopefully that's okay to everyone. Yeah, so now it's the question time. So just raise your questions.
Hi, Colin. This is Mehran Azimi from Endeavour Energy. My question is, based on your experience, when you're replacing the suspension towers, is it, like for like, or using these days like a steel pole or concrete pole, which is becoming more like a cost-effective in a way? What is your view on that?
Yeah, no, I'm flexible there. It really comes down to the authority, what they'd prefer. If you're not climbing towers anymore, which seems to be the go, I don't see why you wouldn't go for the best value. And the best value would be to achieve the outcome of a suspension structure, and I'd be certainly pushing towards more poles than self-supporting steel towers.
Thank you.
It's Danny here from Ergon. Question about you focus obviously on the above ground presentation here, and you're saying marrying that in with your below ground. I'm in the design space, not in the maintenance space, so I'm not entirely familiar with our inspection regime. We do have a number of towers, most have been gifted to us from PowerLink.
Yep.
So what sort of regime are you thinking there for your underground in comparison with your overhead, sort of years-wise?
Yeah, look, below ground, it really comes back down. There's such a variety of different footings that you get. If it's steel encased concrete
understanding that we have a lot of acid sulfate soils around the state, and I don't know what your experience is with acid sulfate soils and whatnot.
No. My previous life was in Endeavour or Integral Energy, and they had a lot of steel towers and acid sulfate soil. It is an aggressive soil, but the below ground, there's a number of ways that you manage below ground. Obviously, monitoring. Usually, you can't quite treat them as the same as a visual rating. Usually, the approach they take is half-cell readings. It's circulating currents below ground, a classic cathodic type deterioration. Once you start identifying the areas where you believe to have the highest level of circulating currents, the simplest way is then to dig up one leg, not necessarily a tension tower, but certainly a suspension tower, and get to an appreciation of what levels of deterioration you're having. That was certainly been the history with a lot of the other steel tower owners, and history's proven that the half style is an indicator at best. A lot of the times they've dug down, they haven't found much deterioration at all, and then in other areas where they haven't been able to monitor, they've found deterioration. So it gets very frustrating. I would fall more towards the anode protection. That is, you put a sacrificial anode in the ground and start repairing or maintaining your steel below ground. There's certainly grillage footings out there that I'm thinking of straight away that people are concerned. Reality is, whenever steel comes in contact with the ground, whether it's a grillage foundation, the deterioration of the top meter is so critical. You must inspect that steel as it goes below the ground. That's where the corrosion, that's where the deterioration will happen. It might need local protection, for example, immediate protection. It might need galvanizing. It might need some form of primer, blasting, repair, even replacement of some of these cords. But the primary steel cords going down as your footings are the ones you want to protect. And anode protection appears to be, from what I understand, to be the best solution you can get. Other than that, you've got to take samples and get a feel for way, one, you can identify the ones to look at, and two, what you find and come up with a protection scheme.
Okay, thanks.
Excuse me, Colin. Another question which we are experiencing from with a few of our projects. Some of these, strength of the tower is not really sometimes to do with the deterioration of the steel. It's to do with the change of standard and vigorous, like a more like a loading which we apply to the towers. So what is your view on that? Normally, in other words, when you assessing the existing towers, which was good for the tower and still in good condition, but it still fails on the with the new standard and with the way it is applied.
Yeah, well, my understanding was that it wasn't retrospective. Is that your understanding as well of the new standards?
That's right, yes.
So the reality is that, I mean, there's ways that it's a really hard one, that one, because, the towers were prepared, the ones we use today, 55 years ago, are completely different standards to the ones that have evolved today. And the way that you model towers is completely different. The way you look at the return periods and the risk factors that go with them is completely different. So all I could suggest there is that I'd use the grandfather clause on all of those assets.
Sorry, what was that again?
I would use the grandfather clause. That is, I would allow the tower to work under the conditions that, when I say the conditions, the standards that were applied at the time. So if you were doing stage 2 of this, or step 2 of this process, you would start modelling the tower, and it really comes down to the utilities, approach it wants to take on risk. You would, if you can sit with the old standards and make it apply. If you want to try to apply the new standards, they won't be up to it. They won't be able to comply with that new standard. So I would be more inclined to use the older towers with the older standards and take that risk on. But that's my view of the world. At the end of the day, the utility's got to manage its own risk, and how it wants to apply them. You might not get the same sort of deterioration. You might only get 10 or 15 years out of the suspensions before you're comfortable to replace them with, for example, a concrete pole. Tension structure is completely different. They've got all sorts of range of loading trees that they've got to comply with. Again, do you reinforce them? Do you use the new standard? I would sit with the old standard personally, but I think if you can get some value and benefits out of that by looking at ways of improving the ratings in certain ways, then by all means. It's not an easy answer, that one.
Yeah. No, thank you very much. Yeah.
It's Danny. Yeah, my experience too, in particular within our organisation, is exactly that, as Colin said. Apply the standards of the day. You can try applying the current standards to that structure, and where whatever augmentation to that doesn't meet current standards, then you've got to bring it up to or replace it with a structure meeting the new standards. I think that's pretty much a common approach Australia-wide under AS 7000 anyway.
Yeah.
Yeah, that is at least in our organization, the view is that if you changing anything on the tower, like upgrading the earthwire, for example, to OPGW, then you need to bring the that tower to the new standard, and then the tower, even without the OPGW, it will phase under the newest standard, and then we have a problem to see how we address that. Hello?
Hello?
Well, that was interesting.
Sorry, I lost, yeah. I thought, I lost yeah.
No, there wasn't much to say about that. That's a challenge.
No, thank you for the input anyway.
Well, sorry, it's Danny here. I know you gave a visual representation today, Colin. What's your experience using LiDAR technology for above ground assessments?
The only LiDAR I've really used has been on existing conductors and veg management. I haven't used it for anything like this. That might well be opening up another area for LiDAR. I haven't used it for that, I'm sorry to say.
Okay. Yeah, I just know we've had a company coming around recently, Position Partners, and showing us their new LiDAR technology for assessments of towers, not towers, but assets and conductors and whatnot, and being able to give you 3D geometry representations of your structures, depending on what accuracy you want to take this study at. I just wonder if anybody's actually started using that for above ground or for asset assessment. I don't know. Yep.
We do have a consultant doing this type of work for us, but not for big scale. So they use the radar to scan through the structure, say that is tower, for example, and then give you a good picture of every single part, including the closure level, so you can make a better judgments on top of that.
Okay.
Silly open.
Any other questions? Well, Colin, I got one for you.
Look, shoot away.
So for the lost cost of the painting, was that based on some theoretical number or the quote for the contractor, or based on some past project cost?
No, it was actually built up by our estimator. They're all developed on the assumption was where you're replacing the structure, for example, the detention towers, which were very expensive, it was based on trying to keep the structures within the easement and keeping power going. Yep. So rather than have rolling outages, which you really can't do if you have to replace a tension, the thought was to, just keeping it simple, take the conductors and the earth wires off the structure, basically prepare footings prior, bring in a new structure and start to build it up, and to allow that you have to find some way of keeping the power going temporarily. There were some temporary bypass structures were being looked at, very, very expensive, awkward. You had to prepare all them before you unloaded the actual tension tower. It's extremely hard when you think they're twin conductors and an earth wire and an OPGW. And that's why we had to come up with some hybrid temporary structures that we could keep the power going while we're working on the tension tower and then bring them back in. So that's why it was so expensive. If you could have rolling outages, certainly for suspension towers, you could replace a suspension tower with a pole in a day. There's no major problems there. If you plan it properly, you could probably do 2 a day. But tension structures were very complex. We were looking at all forms of temporary bypasses, modifications, trying to free up the tension tower to allow a new one to go in. And as I said, it was $600,000–700,000 for most scenarios. So it was a hypothetical. It wasn't an actual project. Our estimator built it from the ground up with an idea, and then worked out the hours and the labour and the cost of the steel and the foundations, and worked it from there.
Okay. Well, thanks for that. And I think the good thing is those tension towers will normally be designed to a higher capacity, so and the performance will be better. So the likelihood of replacement is lower than a suspension one.
True. Yep.
Cool. All right. So now it's 20 to 2. If we don't have any other questions, so thanks, Colin. That was really good presentation.
Sorry, Colin. Hello, this is Mehran Azimi. Just, is it possible to have a copy of the presentation by any chance?
Of course.
Yeah. Thank you very much.
Bing will take care of that.
Yeah.
Okay.
I got a copy, and I'll pass out to the NGN member list.
Thank you.
Cool. Thanks everyone for attending.